Hi students, we have finished our first lecture on application of derivatives. In that we studied about tangents, normals, rate of change of one quantity with respect to the other and approximation. In this lecture we are going to study about monotonicity, which is based on the concept of increasing and decreasing functions. We will also study the properties of increasing and decreasing functions and how this helps us to make a comparison between two functions. Now I'm getting very excited to start this lecture, aren't you? So why waste time? Let's begin. So first of all, what does monotonicity mean in general? In general, monotonicity means succession of words uttered in a single tone. So if I say, hi students, what are we going to study today? We are going to study monotonicity. What does that mean? You can clearly note that all the words which I have uttered are in a single tone. There is no fluctuation, there is no variation in the tempo or no voice modulation. But if I say, hi students, what are we going to study today? Yes, we are going to study monotonicity. Now you can clearly note that I had a change in the tempo, change in the pitch, and there is voice modulation. So something that has a constant behavior throughout is called as monotonicity. Sameness in the sound, style, color or manner could be called as monotonous. In general, at times we call some dull or boring behavior as monotonous. But let us see what does that mean in mathematics. In mathematics, monotonic functions are those which are purely increasing or purely decreasing throughout its domain. So, functions which have the same nature, that is, either they are purely increasing or they are purely decreasing throughout their domain, are called as monotonic functions. Monotonic in the sense they have the same nature. Now, monotonic functions can be divided into two categories, that is, either they are increasing or the second is they are decreasing. Again, in the increasing category, they have been subdivided into strictly increasing or non-decreasing. And similarly, in the decreasing category, they have been further divided into strictly decreasing and decreasing or non-increasing. So one by one, we are going to see the nature of these monotonic functions. So the first type is increasing functions. In that we have the first one, strictly increasing function. Now what is a strictly increasing function? If x1 and x2 are points in the domain of fx such that x1 is less than x2, then if f of x1 is less than f of x2 for all x1 comma x2 in the domain of fx, then such a function fx is called as a strictly increasing function. So it means that the function is strictly increasing throughout its domain, such that if I take any 2 points x1 and x2 such that x1 is less than x2, then the value of f of x1 should be less than the value f of x2. Let's try to visualize it. Now we see that x1 is less than x2 and f of x1 is less than f of x2. So for a strictly increasing function, f of x2 must be greater than f of x1. Now if I take any point in between these 2 points, let us say that this is x3, then we clearly see that f of x1 is less than, let us say this is f of x3, then f of x1 is less than f of x3 and which is less than f of x2. So for a strictly increasing function we have this nature, that is, it is increasing constantly throughout its domain. Now as fx is a strictly increasing function, therefore f of x plus h must be greater than f of x. Here h is any positive value. Now if I take the limit of this expression, that is f of x plus h minus f of x divided by h, when h tends to 0, this would be a positive value. Why? Because this expression is positive and this is also positive. So the limit of this expression would be greater than 0. But this expression is nothing but f dash x. So f dash x is greater than 0 for a strictly increasing function. Thus we can say that if f dash x is greater than 0 for all x in the domain of fx, then fx is a strictly increasing function for all x. So the condition for any function to be strictly increasing is f dash x should be greater than 0 for all the values of x in the domain of fx. Now we can have different types of strictly increasing functions. The first is concave upwards. So a strictly increasing function which is concave upwards. The condition for this is, first of all, f dash x should be greater than 0 because otherwise it won't be a strictly increasing function. And secondly, f double dash x should be greater than 0. That is, the double differentiation of fx should be positive. Then we can clearly say that fx is strictly increasing and concave upwards. What is concave upwards? It is of this nature. It opens upwards. So for this type of strictly increasing function, the condition is f dash x should be greater than 0 and f double dash x should also be greater than 0. The second type of strictly increasing function is f dash x is greater than 0 and f double dash x is equal to 0. That is, the double differentiation of f double dash x is equal to 0. Then in such a case, fx is strictly increasing because f dash x is greater than 0 and it is a straight line with a positive slope. So this is represented in this graph where this represents fx, and the condition here is f dash x should be greater than 0 and f double dash x should be equal to 0. So this represents a strictly increasing function where f double dash x is equal to 0. The third type is concave downwards. So if f dash x is greater than 0 and f double dash x is less than 0, then fx is a strictly increasing function and is concave downwards. So this is the nature of fx. It is concave downwards if f dash x is greater than 0 and f double dash x is less than 0. So for such case, we say that this function is strictly increasing because as f dash x is greater than 0, and it is concave downwards because f double dash x is less than 0. The second type of increasing function is increasing or the non-decreasing function. Non-decreasing means that it is increasing or is constant at some points, but it is not decreasing. So the condition for this is if x1 is less than x2, then f of x1 is less than equal to f of x2. This is the same as strictly increasing function with the exception that there is an equality sign as well. F of x1 is less than equal to f of x2. That is, f of x1 is less than and equal to f of x2, but it cannot be greater than f of x2. So for an increasing or the non-decreasing function, if x1 is less than x2, then f of x1 is less than equal to f of x2. So let's try to understand this. So this is the graph of y equal to f of x. Here we see that for this portion it is strictly increasing. For this portion we see that this is constant, and for this portion this is again strictly increasing. Now here we say that this is a point x equal to a, the value of y for which is f of a, and for this value is f of b. We clearly see that f of a is equal to f of b, and this entire portion is a constant function. This is constant. So for this portion it is strictly increasing, and similarly for this portion it is strictly increasing. Thus this is an overall increasing function. Here we see that for the points which are less than a, it is a strictly increasing function. For points between a and b, it is a constant function, and for the points that are greater than b, this is again a strictly increasing function. So overall this is an increasing function. That is, it is not decreasing. It can be a constant function for some interval. So fx is an increasing function in this case. Now the second category of a monotonic function is the decreasing function, and in the decreasing function there are again two categories: the strictly decreasing function or decreasing or the non-increasing function. So first is the strictly decreasing function. If we say that x1 and x2 are the points in the domain of fx such that x1 is less than x2, then f of x1 is greater than f of x2 for all x1, x2 in the domain of fx. So a strictly decreasing function is such that if we take any 2 points x1 and x2 in the domain of fx such that x1 is less than x2, then f of x1 is greater than f of x2 for all the values of x1 comma x2 in the domain of fx. So let's try to understand it with more clarity. Now let us say that this is the graph of y equal to f of x. Now if we take any point x1, then the corresponding value of y would be equal to, now if we take any point x2 such that x2 is greater than x1 or x2 lies on the right hand side of x1, then the corresponding value of y would be f of x2. Now here we clearly see that f of x1 is greater than f of x2. So this is a decreasing function for all x1 comma x2 in the domain of x. We can take another point x3 such that x3 is greater than x2 and the corresponding value of y is f of x3. Then also we see that f of x3 is less than f of x2, which is less than f of x1. Now we see that this is a strictly decreasing function because the value of fx is decreasing with increase in the value of x. Now we have seen that fx is a strictly decreasing function. Therefore f of x plus h would be less than f of x. Also f dash x is equal to the limit of this expression, that is f of x plus h minus fx divided by h when h tends to 0 would be less than 0 because this expression is 0 and this is positive. So overall this expression would be negative, and hence we can say that f dash x is less than 0 for all x in the domain of x for a function to be strictly decreasing. Thus the condition for any function fx to be strictly decreasing is f dash x should be less than 0. Let's look at the different types of strictly decreasing functions. Now again they have got 3 categories. The first is concave upwards. Now if f dash x is less than 0 and f double dash x is greater than 0, then fx is a strictly decreasing function and is concave upwards. Now this represents the curve y equal to fx. We see that this opens upwards but is a decreasing function. Thus the condition is f dash x should be less than 0 and f double dash x should be greater than 0. The second type of strictly decreasing function is if f dash x is less than 0 and f double dash x is equal to 0. Then in such a case we say that fx is a strictly decreasing function but is actually a straight line with a negative slope. So this is the graph of y equal to fx. Actually it is not a curve, it is a straight line, and we see that the slope of this line is negative. So f dash x is less than 0. So the condition is again f dash x should be less than 0 and f double dash x should be equal to 0. The third kind of strictly decreasing function is concave downwards. Now for this to happen, f dash x should be less than 0, which is actually the required condition for a function to be strictly decreasing, and f double dash x should be less than 0. So if these conditions hold, then fx is strictly decreasing and is concave downward. So let's see the graph of it. This is the graph of y equal to fx, and we see that this is concave downwards. So if f dash x is less than 0, then it is a decreasing function, and f double dash x is less than 0, then it is concave downwards. That is, it opens